It's not. You see it in a correct way?
We see also the next slide on the side.
Yes, that's better, I suppose.
Yes, that's better.
Perfect. So thank you already for the nice introduction. So my name is Caroline Detender. I'm a professor at the Department of Biochemistry and Microbiology at Gent University, as has been said previously. We recently started a project to look into microplastic contamination in soil ecosystems. And in fact, we see that there is a quite big need because we get invited quite a lot to give talks about this topic, as we are almost the sole research group working on this topic within Belgium then specifically. And maybe for those of you who speak Dutch, we recently also gave a talk in a podcast episode, which is called the Microcast. So this is normally a podcast that focuses onto microorganisms in general in different types of environments. But they also find it a very nice way, because the micro is also into the name, to also have the topic of microplastic pollution in here. And the podcast is very nicely introduced because the person who gives the talk needs to set up 3 or 4 different questions, of which one is not true. And I'm going to present you the questions that I gave, and I hope that at the end of my talk that you also will be able to really find the one that is in this case not true, so the untrue value. The first one is microplastics are in fact all plastic particles that are smaller than 1 millimeter. So especially those particles that are not visible by the eye. The second one is microplastics can be formed especially by physical disruption or by fragmentation by microorganisms. Then the third one that we are having is that microplastics can have negative effects, but can also have positive effects on plant growth and on the plant's soil ecosystem in general, in fact. And then the last one is 1 apple contains more plastic fragments than comparison 1 kilograms of mussels. So maybe keep those different questions into your mind, and hopefully you will be able to answer it by the end of the talk. But bringing us now to this question. So when I look up plastic pollution in general, just on Google, for example, these are all type of figures or pictures that I rather see. So in most cases, we see a lot of different pictures appearing that is regarding to plastic pollution in beaches, on the ocean, of marine wildlife, or to even protest actions about plastic particles that are found in marine environments. So in general, the public attention is drawn a lot to the marine pollution. And therefore, there's also a very high public awareness about plastic pollution in marine environments. And of course, this is also necessary. When we, for example, compare all of the plastic waste that is generated, around 0.5% of the plastic waste in the end will reach the ocean and the seas. And it will definitely have its consequences. You have the filter feeders, like the mussels, the oysters, that will ingest the smaller particles by which it comes into the food chain. But we, for example, also all know the pictures where you see, for example, turtles that are trapped within plastic waste, or, for example, of the whales that will ingest plastic bags by which it gets into their stomach, and by the end that they can starve to death. So indeed, the problem there is quite high. If we compare it, for example, to all of the plastic waste that is produced in here, you can compare it to about the weight of 3,500 whales, about 285,000 elephants, or if you really go back to the soil, over 2 billion amounts of earthworms that are present in here. However, this plastic waste, we have indeed 0.5% of the global plastic that eventually reaches the ocean, but there is much more that is mismanaged. About 23% of all the plastic waste is in fact mismanaged. And when you look it up, you see that 19 million will eventually leak into the environment. If you then compare it to the 1.7 million that is transported to the ocean, then we still have more than 70 million of waste that is present within our environment. About 6 million of those are leaked to the rivers, to the coast, so still a bit more into the marine environment, to the freshwater environment. But taking this all up together, we still have about 12 million of plastic waste that is present there. And most of this waste is in fact present into our soil ecosystems. And when we then, for example, also have a look into the number of publications that are written on the problems that plastic and also more specifically microplastics have on soil ecosystems, we see that this is limited, very much limited compared to a marine and to a freshwater environment. If I say to you that the first publication on microplastic pollution has already been written in a marine environment in 1972, in a comparison, in a soil ecosystem, the first research article there has been published in 2016. So this is a research gap of about 40 years, which is quite tremendously. So there is something happening there, which leads that we have now still a big misunderstanding, or we don't know a lot about everything regarding plastic pollution and microplastic pollution in soil ecosystems. And up to today, so this figure only goes until 2021, but even up to today, only 10% of the publications that are written about plastic pollution, and more particularly microplastic pollution, are in fact focusing on a soil environment. And from these 10%, about 8% are in fact reviews of reviews of reviews. So there is only 2%, especially of real novel articles that are appearing on microplastic pollution in a soil ecosystem. Now, one of the main difficulties that we are having is that plastic is a very big word. You can classify plastics on several ways. First of all, and I think the most known one, is that we are having different types of polymers. We can think about the PVC, for example, the PET bottles that are quite well known, but also polypropylene, which is a very steady plastic and is used especially when we need to have hard plastics, polystyrene, but also, for example, nylon, which is specifically used in clothing. And then something that is not even represented in here are all the different types of bioplastics, like a PLA or a PBAT. So in this case, we are already working with a lot of different types of polymers that are all classified under the common name plastic. But second of all, we also have the terminology based on size. Most researchers focus somewhere between the microplastic, mesoplastic, or the macroplastics. Mostly, they define microplastics as all plastic particles that are smaller than 5 millimeters. However, currently we see that there is more progression and that they define it now more and more to microplastic particles as all plastic particles smaller than 2 millimeters, in fact. Because 5 millimeters can still be seen as a quite large substance. And these are now categorized more into the mesoplastic classification, where we have 2 millimeters up to 2.5 centimeters, and everything that's even larger is called a macroplastic. And you will see these three different definitions also coming back, because the main story that I'm going to tell you today is really going to focus on these microplastics, but we also have looked particularly to the mesoplastic and to the macroplastic as well. Now, if I continue my story, this is a picture where that is gathering all the different experiments that have been conducted on microplastic measurements in a marine environment up to 2021. And as you can see, especially for the coastal areas, we have already a quite a lot of studies that have been conducted and a quite good idea about what a microplastic concentration might be in a particular region or not. As told, this is especially into coastal areas. So from the deep sea, for example, we also don't have a lot of measurements, and that's just based because of practical issues. It's much easier to sample very closely to coast than when you're going to sample in the deep sea environment. What we also noticed, for example, here in Europe, that it seems that our microplastic pollution is lower compared to, for example, if you compare it to China or to New Zealand and so forth. Especially here for us in the North Sea region, this is quite logical because we have a very strong current which will drive our microplastics, in fact, to other parts in the oceans and the seas. So it's maybe not due to less pollution from our side, but especially due to the currents that are facing there or that are having there. If we then compare this to the number of studies that have been conducted on microplastic contamination in a soil environment, we can see that this is much more limited. Most studies have been conducted in China, where we can see that there are even much bigger numbers present of microplastic pollution in soil, even when we compare it to these coastal areas. But especially for Europe, a lot of studies are missing. So in 2021, 2022, we had about 4 different studies. Now some more have occurred. So I think we're now about to 6 to 8 different studies, maybe even up to 10. But still, compared to marine environment, this is quite limited. So we don't have a good idea at this particular time what the microplastic concentration is in our soil environment, especially not if we can compare it then, for example, to the marine environment. And as you can see here, here in most cases, we always report, as told already by Elke, our microplastics, especially by items per kilogram. And this is just merely due by the measurement technique that we are using. In fact, there are different types of measurement techniques, but in most cases, we work with more fluorescence microscopy techniques, for example, or a micro FTER technique. Which is always going to report the microplastics in a number rather than a weight. Now we can also really have a look about how many microplastics are present there, but then the next thing that we can ask ourselves then is what are these microplastics doing in our soil environment? Are these going to be having an effect on our plant ecosystem, on our nematode community, on earthworms, and so forth? And also this is still a big question mark. Not a lot of publications have been presented, still a little bit more than when we look, for example, to the microplastic concentration. But the strange thing is that a lot of these studies contradict each other. There are studies that are showing that we have an increase in plant growth, for example, by the presence of microplastics, something that we would not expect because you would rather think that we see a negative result of these microplastics present and that we see either a decrease of, for example, the root and the shoot growth. On the other way, also, for example, the nutrient content in the soil can be changed, or the water retention, where we can either see an increase in water retention or an increase of either water evaporation. So also here there is a little bit of contradiction. The only thing that we do know and that all studies agree on is that when microplastics are present into the environment, that we see a decrease in the soil biodiversity. And in the end, this can have tremendous effects on our total soil plant microbe interactions as well. So this is also something that we need to think of. And then before we started this project, we asked ourselves the question, okay, what can be now the main reason of this contradiction? Why can we not decide what the main effect is of these microplastics? Well, first of all, this is due to this limited number of studies. Up to now, we do not know what the concentration is of our microplastics. The studies that show, for example, a very big negative effect have used concentrations, if you recalculate it, where you're going to have a concentration of 50% of or either 60% of your total soil environment, that's going to be microplastics. Of course, if you're going to change your soil particles by 50%, this will have an effect on your soil composition and on your plant afterwards, because you cannot speak anymore of just a mere soil by then. Second of all, we also don't know which different polymer types are present. As I told you already, plastic is a common name for different types of polymers. And each of these polymers can have a different effect on our plant ecosystem. It can be, for example, that a polyethylene will have a negative effect on the plant, while a bioplastic, for example, will have no effect or maybe even a positive effect. Because these bioplastics are in most cases, or in certain cases, can be broken down by microorganisms and maybe can even release nutrients into the total soil ecosystem, which can cause, of course, nutrient release, plant growth promotion. So also here we need to ask ourselves the question, which different polymers are present into our environment. Then third of all, we have the size ranges. The microplastic is a very big name. So you have microplastic particles of 2 millimeters, which is quite a big size, but you also have microplastic particles of 1 or 2 micrometers. And these different sizes will also each have a different effect on our soil ecosystem, on our plant ecosystem. And in the end, even the shape can play a role. Nylon is in most cases, for example, a fiber, but you can also have more a pellet form or something even completely else. So all of these different things need to be taken into account when we are going to look into the effects of our microplastic particles on our plant ecosystem and on our soil ecosystem. So that's why we wanted to start first with this. We first wanted to do a monitoring to decide what the average concentration is, the polymer types, the size changes, and the shape, before we can move on to the effects on the plant and the soil ecosystem. And that, in fact, brings me to the topic of today. So this little pop-up talk where we are going from the measuring and the monitoring of microplastics in soil to go eventually to the effects of those microplastics on the plant and the soil ecosystem in general. For this, we have the Micos Project. The Micos Project has started in August 2023. So we are now working for a little bit more than 1 year. And for those of you who are interested in the project or want to know a little bit more, I would advise you to go to the website www.micos.ugent.be, where you can also subscribe to our newsletter. Our newsletter will appear about every 3, sometimes 4 months. And you will see that it is very low key because in the large scale measurement, a lot of farmers have also participated. And we also want to report our data to the farmers in a way that it's also understandable for them. But in fact, during this newsletter, we also keep everyone updated about the recent progress into our results. The Micos project itself will consist, in fact, about 3 different stages. We are now especially working into the first stage, which is called the risk assessment. And into the risk assessment, we really want to know how many microplastics are present at this particular time in agricultural fields in the Benelux. For this, we have set up a large-scale measurement to really measure these microplastics. And I will talk about this later a little bit more. But to be able to measure these microplastics, in fact, we first of all also needed to optimize a method to measure microplastics into the soil environment, because this is the hardest or the bottleneck, which is the reason why we have not a lot of studies, especially focusing on microplastic pollution in the soil environment. Once that we have this and we have an idea or we know what the average concentration is, for example, of our microplastics into the soil environment, we will move on to the second stage where we are going to risk-based testing. What are the risks for our plants, for our soil health, when a certain concentration of plastics into with particular polymer types that are present through our soil environment? And then we also have a third stage, and in the third stage, we also want to go to risk reduction. How can we prevent, for example, the introduction of microplastics into our soil environment? And for this, we are focusing on plastic degrading microorganisms like a bacteria, a fungi, but it can even go up to a nematode, for example, where we are going to see if certain types of bacteria can degrade certain types of polymers, and then it can be used maybe later onwards. I'm going to say something into compost manufacturing. The Micos team is now consisting of 4 people. Of course, myself, I'm the coordinator of the project. Then we also have Dr. Lisa Joost, who is a postdoc of the group, who is in charge about all the communication, but also everything about soil health and soil measurements. Then we have 2 PhD students, Bente van Buiten and Josephine Meulenaren. Bente van Buiten is especially focusing onto these first 2 work packages, which is the method optimization and the large-scale measurements. And Josephine is especially focusing onto the risk-based testing. So she recently started in September, and she's now optimizing this. And the 2 together will also focus onto the plastic degradation. And with this, I'm now going to guide you a little bit step by step through our different work packages and what we have already done. And I'm very proud to say that the method optimization is already done. So after 1 year of research, we were able to have a method where we can measure microplastics in a quite good, cost-efficient way in a soil environment. And we are also testing it now, for example, on compost, where it also has up to now very good results. So we are quite happy about that. Now, the first step is quite easy. There we are going to sieving. So after that, we have collected our soil samples, for which I'm going to tell you a little bit more later how we have done this. We first are going to sieve our soil over a sieve of 2 millimeters so that we get loose of all the bigger microplastics. Because as I told you, we define a microplastic of all plastic particles that are smaller than 2 millimeters. So the smaller particles normally will get through the sieve, the bigger particles will stay on the sieve here. Then in a second step, we are going in fact to a pre-oxidation. You will see that we have a second step of oxidation, and this particular step is necessary to remove the organic matter. Why do we need to remove the organic matter? Because organic matter will have the same density as our plastic particles. And in the next step, what we are going to do is a density separation. With the density separation, we are going to include sodium iodide to our soil, and our soil will stay on the bottom of our layer, but our plastic particles, they will start to be floating because their density is lighter than our sodium iodide. It's between 1.4 and 1.6 gram per cubic centimeters. But also the organic matter has in most cases a similar density or a lighter density than our sodium iodide, and therefore will also start floating. So therefore we first need to remove as much as organic matter already, so that in the end, if we are going to density separation, that we don't have too much organic matter that also starts floating together with our plastic particles. To remove the organic matter, we do a pre-oxidation, and for this we use hydrogen peroxide, as you can see here, in total 25 milliliters and at a concentration of 30%. And we keep it there for about 3 days. So the reaction really keeps on for multiple days, and you really see the degradation of the organic matter, as there is a lot of also oxygen that is going to be released once the hydrogen peroxide is added to the soil. Once that this organic matter is degraded, as I told you already, we go to the density separation, and by this we will have a shift between the soil particles and the plastic particles that are present in here, and the plastic particles will start floating. However, after that, so here also you see the density separation again, and as you can see, the density separation is conducted 3 times. Why do we do it 3 times? Because there will always be some plastic particles still left in the soil after that we have added it once. So to be able or to remove as much of the plastic particles from the soil as possible, we therefore do this density separation 3 times so that we are quite sure that we have removed most of those plastic particles. Also, when we do such type of process, we always take one positive control with us. A positive control is a soil sample where we add or where we are going to spike by ourselves fluorescent labeled microplastics, which we later on want to retrieve again, so that we are quite sure that we have a good recovery of our microplastic particles. Good recovery for us means that we can find back those spiked particles for 95% of the cases. We will always have some loss of plastic particles, especially from the smaller one that can stay stuck, for example, into the soil particles or onto the enamel or on the other glassware that has been used. In another step, we do another oxidation, again to remove as much as organic matter as possible. And as you can see, this second oxidation is still necessary because at the left, you can see 2 filters that are used before this digestion with the Fenton reagents, and at the right, the ones after the digestion. Now here you can see that most of the soil particles have been in fact removed, but next to the plastic particles, which can be here seen because this is also spiked sample, so the plastic particles are here seen as the white fragments that you can see up above. You see a lot of organic matter that is still present. And after the oxidation with the Fenton reagent, you can see that a lot of this organic matter has been broken down. And now it should be normally easier to find those plastic particles also back. What we in fact want is we want to see something like this in a control way, where you can have on your filter a very easy overlook of the different plastic particles that have been found here. This filter that I'm showing you here is a filter of a water sample. So a typical marine sample or a freshwater sample. As you can see there, the case is just much easier. You don't have as much as organic material present in a water column, or even almost none, by which it is much easier to immediately filter your water over your filter and count your number of plastic particles. And that's what makes it so hard for the soil environment, but also for a compost or a digestate or a slurry. The organic material is present in such high concentrations that it makes it very, very difficult to measure your number of plastic particles. Because, and that's what we are going to see within a few minutes, this organic material will also interfere the counting of your plastic particles, because it is very easily mistaken both on a micro FTR or under a fluorescent microscope as a plastic particle. So sometimes an organic organic matter will be counted as plastic, which we of course don't want. So therefore, again, it's very necessary that we remove this organic matter as much as possible, also to make the counting of the plastic particles possible. Now, after that, we have this filter, and I've now shown you one of the two worst filters of so this one is of a compost sample, and the right one is of a soil sample with really a high amount of organic matter, maybe from the people from the that are present here from the Netherlands. This is a sample that comes from Flevoland. It was the it was a soil type where we found the highest organic matter, which was 3 to 4 times higher even than a normal Belgian soil that we could find. So these were the worst for us to deal with, and we were very happy already to see this type of filter to work for, that we can proceed further with. The next thing, once we have this filter, is we are going to add the Nile red. And this is where we differentiate ourselves compared to other labs. So in most cases, when you get this filter, we are proceeding towards a micro FTR machinery where we really are going to measure also the plastic particles, and where you can decide which polymer or which plastic is which polymer. However, the drawback of this micro FTR technology, although it works very good and it is a good esteemed method, it's very, very well established, is that it's going very slow and it's quite costly. So it's not, you cannot use this, for example, if you want to screen a lot of different samples at the same time, which we have. Because in total we are screening now 1,200 samples. That would not be possible to do this all on a micro FTR. This would take us about 3 years with only one lab technician. So therefore we need to go to another way. And what we have to do now is we are going to stain our plastics with Nile red, as you can see here. And this Nile red will bind both on our plastic material, but also in some cases on organic matter. But by then, after the staining with the Nile red, as you can see here, we will lay our filter under a fluorescent microscope under 3 different filters: a UV filter, a blue filter, and a green filter. And this UV filter, blue filter, and green filter, in each case will show a fluorescent signal from either the plastic or in some cases also from your organic matter. And each of this staining will also be related towards a real number. And this number of fluorescence that we will find back will be put into 2 decision tree models. And with this decision tree models, which are in fact hidden Markov models, we make sure, or we can make a differentiation between plastic and organic matter, but also between different plastic polymers. And that's what I'm showing you here. So here we have our 3 different filters, our UV, our blue, and our green. And as you can see, our PET particles will light up very brightly, for example, under each of the 3 different filters. While, for example, when we make use of high-density polyethylene, you can see that it lights up, but not that intense under UV filter. It lights up very intensively under a blue filter, and it will not be shown under a green filter. Same goes for PVC. There, the highest intensity will be shown under the blue filter, but also very high intensities under the UV and the green. And then we also have our nylon. Well, for example, for the non-plastic material, you can see especially on the UV filter that there is also some fluorescent signal that is going to be measured. Well, under the blue and under the blue and the green filter, this is almost not present. And that's how we make our first distinction between what is plastic and what is not plastic. So in most cases, organic material, by looking at those different intensities of our fluorescence. But then second of all, we are also able to distinguish different types of plastics. And we can do this with a certainty now of about 89%. So with 89% certainty, we can say, just based on the fluorescent signal, if we are looking into a polyethylene fragment, a polypropylene, a polystyrene, a PUR, a nylon, PVC, or a PET. This model has been, first of all, built especially for plastics that are present into a marine environment or a freshwater environment. So therefore, we expect that in our case, also other plastic materials can be present. Therefore, some of our samples will also be measured under a micro FTR so that we can find these. But we will already include in this random forest model the biodegradable plastic, especially PLA and PBAT, as these are quite highly used in agriculture. And we think that we are going to encounter these as well. So we are going to increase this random forest model, in fact, up to even 12 different plastics. And what we also want to include is an uncertainty factor, so that also the model gives back if he doesn't know which type of polymer it is, so that we can further on really under an FTR or with Raman spectroscopy really decide which type of polymer that we are looking at. So that's in a nutshell, in fact, our first work package, the method optimization. So with this, we are almost finished. Everything in the lab has been done. The only thing that we are still doing is we are still improving this random forest model so that we can include more and more polymers. And for that, Bente is doing that at this particular time. Now, this method optimization was, of course, necessary because we did our large-scale measurement. And for that, I'm going to show you in the next slide how we have measured or how we have taken our samples, which samples that we have taken, and also give you already a glimpse of the first results. But first, if we want to measure microplastics on the field, where do we need to start? Well, in fact, we wanted to measure microplastics on 240 agricultural fields in the Benelux. When I first wrote this project, I wanted to do this over the whole of Europe, but the problem was if we wanted to do that, that would be, first of all, very difficult to really find fields over the whole of Europe and to sample it ourselves. But second of all, we already see a lot of diversity in the fields just in the Benelux. Between the Netherlands, between Flanders, and between Wallonie, for example, there is already a very big differentiation into nutrient content, into soil texture, and this will, of course, already have its impact on the microplastic content as well. And therefore, we decided to not stick to Belgium solely, but to do it in the Benelux, so that we have already different types of soil structures present, but still keep it in a limited way. Now, when I'm saying this with agricultural fields, I'm really talking about fields with crops, so not permanent grasslands in this case. So really fields where we have grown maize, for example, or lettuce, or strawberries, and so forth. Now, one of the first things that we needed to do is we needed to find those 240 agricultural fields. And this was one of the first main challenges that we encountered. How can we find farmers that wanted also to be included into our research campaign? We had at Flanders at that particular time the PFAS crisis, also in the Netherlands. So there were a lot of farmers that were not very happy or willing to also join this particular project, because they were, of course, also afraid that also the microplastics might have a consequence in the end. So we started first with the first thing, and that was designing a website. Of course, with a website alone, you're not there. So we started then a communication campaign where we went to the local radio. We were especially at news articles like in Boer en Tuinder or at Plattelands TV in Belgium, for example, to really find or to really speak to the farmers and say why this research was necessary and how they can contribute. Well, we also really went to, for example, werktuigdagen, tuindagen. So these are fairs that have been given in Belgium, but also in the Netherlands, to really find farmers to subscribe for our particular project. What we also did was we reached out to partners in the Netherlands. So there we work together with NEO, and also in Wallonie we work together with CRAW, and in Luxembourg there we had the immediate contact with ASTA that works for the environment. It's work for the government, so which also helped us to find enough farms. And this also paid off. So as you can see here, we started in fact a little bit before October 2023 to find our 240 fields. Here we launched our website and we went for the first time to the trade fair in Belgium. In black, you can see the total number of fields that we have or that have been subscribed through our website. In green, it are those in Belgium, in orange, those in the Netherlands, and in pink, we have in Luxembourg. For example, when an article was shown in Landbouwleven, you can immediately see that there was a high increase in the number of subscriptions. Same goes for Wild, also for the Plattelands TV. And what we had here is that we have here encountered a very big increase because here we had a contact with the people from CRAW who really find for us, especially the farmers in Wallonie, so the southern part of Belgium. The same goes here. Here we contacted, for example, the farmer consortia in the Netherlands. We also went to a trade fair. And in the end, this resulted in 9 parcels from Luxembourg, 79 parcels subscribed from the Netherlands, and 333 parcels in Wallonie, which left us to 422 parcels in total, which was very nice because we only needed 240 parcels. So this means that we had over to almost 200 parcels more, which was very nice because for this, then we were also able to make a decision which parcel we wanted to include or not. What was very clear that it was much more difficult to find people from the Netherlands to subscribe. It could be because as Belgian, it was a bit harder to find those, but with the farmers that we were able to speak, they also really told us that at that time there was already a lot on their plate with everything about the nitrogen that they needed to have a look at, and just having another survey on another contaminant was a little bit too much for them, which was of course also totally understandable. But that's the main reason why we have less parcels in the Netherlands compared to Belgium. But in the end, our campaign was a success. We had over 400 parcels, and then the next question was, okay, how are we going to select those 240 fields? Well, each of the farmers, when they subscribed themselves on our website, they also need to fill in some additional information. We asked, for example, what type of irrigation was used on their parcel, but also, for example, which type of soil texture that describes for themselves the best. If they use compost, if they use a type of manure that was present, and so forth. So we had a high amount of additional information. And this additional information was in fact used to set up a risk assessment score. So based on what could be found in literature, we made a risk assessment where we looked into the location of the field, the soil texture, and the soil treatment. For example, fields that were closer located to industrial areas, to cities, to garbage patches, or to highways got a higher score compared to the ones that are further located, just because there is the idea that a higher amount of garbage will be present in there. Also for the soil texture, we took this into account. Why? A sandy soil is, for example, a little bit more water transparent, while a clay soil not. So it could be that in a clay soil, that especially in the top layer, because we focused on the top layer of our soil, a higher amount of microplastics will stay there. However, it can also be the other way around. There was not a lot of literature, so this was just a mere guess from us. But also for the soil treatments, we need to take this into account. For example, for compost, if compost has been added, we said, okay, then the risk is going to increase with +5 because we know that compost will contain some plastics eventually. Same goes for manure, but also different types of irrigation system, and especially the use of plastic mulching will have increased every time the risk. In total, you could have a risk between a value of 0 and a value of 100, but the value of 100 is very hard to reach. So in the end, we divided it like this. So the soils with a very low risk got a score between 0 and 24. The ones that have an increased risk score between 25 and 34, the ones with a high risk between 35 and 44, and the ones with an extreme risk over 45, score of over 45. So in total, we had 4 different categories that we had to look at. We needed to have 240 fields. So we wanted to select 60 fields in total of each of these categories. And we were also able to do that. And even more, we took into account an additional factor, and that is the location of our fields. Because for example, for Belgium, we didn't want to work, for example, with the provinces, as you can see here, because next to the provinces, you also have the different types of soil textures. And this is in fact the map that I'm showing here, where you have the different types of textures of soil that is spread throughout Belgium. And what we did, we selected, in fact, so as you can see, so these are the total number of subscriptions. There were a lot of people, for example, who subscribed here, which is in fact all different types of soils with a more loam part. And also here we have the sand loam. And these 2 areas, so both sand loam and loam, are known that they have a very big agricultural setting. And that's therefore also very normal that we had a lot of subscriptions. While for other places, for example, like here, there were in fact 3 different regions where we had no subscriptions, but these are in fact quite logical because of 2 of them, they are known for their permanent grasslands, and that was also something that we were not interested in. And then in the Hoge Ardennen, as it is shown in here, these are really mountains. So also there is almost no agricultural activity. And then based on this risk score assessment and also those different soil textures, we were then able to select in total in Belgium these different types of soils. The same goes for the Netherlands, but there we worked with pedoclimatic regions, which have been constructed by our partners at NEO. And also for them, we in fact were then able to divide or to decide different zones. So these are also the subscriptions that could be seen. And also here we took into account this risk assessment score. And this, so that in the end, we have 70 soils subscribed in the Netherlands, or we have sampled 70 soils in the Netherlands, 100 in Flanders, 60 in Wallonie, and a total of 10 soils in Luxembourg. So this gave our eventual selection of 240 agricultural soils. Let's then move on to the field sampling. So once that we have our soils, we of course still need to sample the fields. And for this, we also should take into account a lot of different measures, because field sampling for microplastics is not the same as when you would go out for sampling, for example, for nutrients. For the field sampling, we were in fact a core sampling team of 3 persons, myself, Lisa on the left, and Bent on the right. But we needed to sample 240 soils, and we wanted to do this within a period of 12 weeks. So this was very heavy because we also didn't only sample for microplastics, but we sampled also for a lot of different other samples. Because we wanted to make correlations afterwards and also wanted to see where our microplastics are coming from. That's why we had a lot of help from different volunteers. Like, for example, here you see me with my father, who also joined me for some of the sampling campaigns. Also the father of Lisa, who is shown here, is involved. Then we had some people from the lab. We even had here Kevin and one of the lab technicians from Ilvo Ostend that were invited. So in fact, people who got used of microplastic sampling, but then in a marine environment. So it was a very nice sampling period. I don't know if you still remember, so from the people who are from Belgium, Netherlands, Luxembourg, somewhere, the spring of last year, but it was very wet. So we had also a lot of rain, but still it was quite a nice period to have this sampling campaign together. Now, how did we sample the fields? So in total, we divided our fields into in most cases a rectangular, if this was possible or not, and we sampled 5 different plots, which we gave an indication of A, B, C, D, and E, for which we always wanted to have the edges of the fields. because there you of course also always have also the introduction from what is laying there. Like for example, in this field here at the other end, you also have a street. So it could be that more garbage from people that are coming by is going to be measured here because of the street. So therefore, maybe a higher microplastic concentration would be found on point A. And then point B was, we always try to settle point B in the middle of the field. And that was then, in fact, our null measurement and a good measurement of our complete field without the influences of the different edges. Now we sampled 240 fields, 5 replicates. So this means that for each observation, we had 1,200 samples. And these 1,200 samples were taken for multiple things. So first of all, for microplastic measurement, one of the main objectives, but we also looked into the to the bigger plastic particles, the meso and the microplastics. Then we also took one sample that has been used for the soil microbiome, for the soil nutrients, and also the soil texture. And these are so that we can later on also correlate the number of microplastics, for example, with the presence of a certain bacterial category, or with, for example, a higher or an increase of pH or a higher nitrogen content, something like that. Or in case if we can also find, for example, a correlation between microplastics and then, for example, a sandy texture, a loamy texture, and so forth. We also measured the penetration resistance, and we also did a field observation. Now, in each of these 5 plots, so A, B, C, D, and E, we in fact, one plot was always 2 by 2 meters that we set out for both the microplastic sampling and the microbiome sampling. What we always did first was there were, in most cases, when we went out for sampling, there were 3 people. The first one that went in set out these plots of 2 by 2 meter and put here small pots of baked soil. That was in fact our negative control. This negative control is necessary because microplastic measurement is really not that easy. You have atmospheric deposition from microplastics. You also have microplastics that are coming from your clothing and so forth. So it can be that at the moment that we are passing by, that we are already contaminating our soils. And of course, we don't want to measure this contamination that we are including by ourselves. So that's why we put this negative control here so that we can measure the contamination that we are doing just by sampling. Once that the person has passed for the field observation and also for setting out these plots, the second person jumps in and that person is going to do the microplastic sampling. And that person was always dressed like this. So you see here a yellow suit. And this yellow suit is necessary because one of the most parts in all of your clothing, you always find a lot of different plastic particles. This yellow suit, it can be that we will also lose some fibers, plastic fibers, but it is such a bright color that it will not be present in really high concentrations in the environment, so that if we would find it back in our own samples, that we probably can decide, okay, this is probably a microplastic scrubbing from the suit. I'm sorry, I'm having a little bit of a cold. So that is probably a microplastic coming from the suit and not from the soil itself. Also, almost all of our material was plastic free. That was also very important. Yeah, sorry again. After the one of the microplastic has passed, then we had the second person, or the last person, and he or she took then the samples for microbiome, nutrient concentration, and also soil texture. In most cases, he or she was also wearing a yellow suit, but that was not necessary anymore because the person for the microplastic sampling has already been passed. And then in the end, completely at the end of the sampling, we also looked into the sampling of macroplastic. And that's been done by just running over the field from field plot A up to field plot C, as you can see, as a zigzag. In most cases, we have 2 people into more or less a width of 6 meters and really searching the soil ground to bigger plastic particles. So that's how the sampling has gone. I told you already about the newsletter. Well, it appears every 3 to 4 months. And we also show them something like this to show where the progress is of those 240 fields. For the microplastics, we just started. So at the beginning of this month, we had the first measurements of the microplastic concentration, which is very nice because we needed to make sure that our method is definitely working well. For the microplastics, we now have all data collected. Also for the microbiome, we're almost halfway. For nutrients and moisture, we are also already halfway, so the bar is already finished. And for soil texture and soil compaction, we in fact also have all our data. So we can start analyzing, and I'm very happy already to show you a little bit of the first results. Maybe first on the soil texture, so that has nothing to do a bit about microplastics. So here you can see all of the textures. There is not a lot of clayish soils, but a lot of, for example, sandy loam, loam soils, silt loam, silt clay loam. And what is very nice is that the farmers also needed to give their understanding about which type of field that they are having. And we have colored the ones that were given the same name by the farmers. And as you can see, most of the farmers can really decide quite well by themselves which type of soil that they are working on, because in most cases it is really falling within one category, the different colors. So in this case, that's also very good because our risk score analysis also has partially been decided based on this soil texture that the farmers gave to us. Then for the microplastics, so we have just started the extractions. How does it look like? I'm showing you here one filter. And as you can see, it's very hard if you should count this by yourself. So each of the, it really looks a little bit like if you should be looking to the stars. But all of the bright red and yellow and greenish particles that you're seeing are in fact all plastic particles. So this is just from one soil where we in fact expected not that much microplastic contamination. I cannot count this here by eye, but I think we are as over 100 microplastic particles. If you know that we measure this on 10 grams of soil, you can already imagine that we have a lot of microplastic contamination present into these soils. So these are counted by the automatic methods. I cannot give you a lot of results yet, but maybe a few of them. So this is of 2 different fields where there is organic and plastic. In fact, it means that we first differentiate between organic material and the plastic material, for example, where you see that the organic material is higher than the plastic material. This has been done on 10 grams of soil, so from one field. And as you can see, we have measures here for example for this field of about 32 different plastics on 10 grams of soil. So this accounts for 3,200 plastics if you would go to 1 kilogram of soil. And if we compare, so the first 2 soils, of course, these are only first 5 soils, but the first 2 soils were soils that were treated every year with compost, while the last 3 ones are not treated with compost. The first thing that we can see is that indeed these soils have, or it seems that they have a higher microplastic load, while for the ones plus also a higher amount of organic material, which is of course a good way compared to the ones that have no compost. Of course, these are only the first 5 measurements, and it doesn't say a lot about the other 235 soils that still need to be encountered, so we cannot draw already conclusions out of these first 5 soils. If we then have a look, we can see that most of the plastics are either decided that it's going to be a PET or polyethylene or a polystyrene. And so these are the soil measurements that we are having up to now. So as said, we do not know now, for example, anything about biodegradable plastics, but that's because we are still adapting our hidden Markov model so that also biodegradable plastics can be found. Then we have the macroplastics, and for the macroplastics, you see here Brent. So he was a master thesis student who helped us out for a couple of months. And what we are really doing is, here you see a lot of the garbage that we found from one particular field. And in fact, we are weighing, measuring, and counting each of these different plastic particles, which is a lot and a lot of work. But the nice thing is that by doing this, that we also have a very good idea about the contamination of the bigger plastic particles onto our fields. And not only on the plastic particles, but we also took into account metals, rubber, glass, ceramics, natural products, and then also everything that has to do with clothing and shoes in this way. Bente, our student, she made a new microplastic classification system, and that is in fact a classification system that has been adapted from the one that is used now by ICES, but specifically for marine environments. But some of the categories were missing. For example, one of the things that we encountered quite a lot, or in some cases, are, for example, plastic shotgun cartridges. Another thing that was present are, for example, plastic animal tags, and another type of synthetic rope, which we can also not find in a marine environment. Something else that she did for the marine environment in size categorization, they started from A and then went to B, C, D, E, and F. But in fact, we found a lot of small plastic particles back. And that's why we also decided to include another format, which is called AA, and which in fact contains all of the mesoplastics. So all of the plastics between 2 millimeters and 2.5 centimeters. So all plastics that fit within this square. And that was also necessary because this was the highest amount of plastic that we could find back. In the end, after the categorization, we got a big Excel file which looked like this, where for each plastic particle that we found back, we decided which litter type it is. We also gave a description about, for example, the color, or if you could find a particular brand, the number of pieces, because sometimes you could really see that it was coming from the same garbage in the beginning, the weight, and also the surface. And for the surface, we did this on this AA, A, B, and so forth categorization that we were having. In the end, this resulted in this. If we look into overall 240 fields, we see that we especially found a lot of plastics, and then the second biggest category was the ceramics. Now, this is in fact an underrepresentation because for some of the fields there was such a high amount of bricks present that it was unable to count all of those. So probably the ceramics also should have encountered a little bit more than what was shown in here. But the other categories are normally, in fact, on the right way counted. If we then specifically look to the plastics, so I'm here showing you again the categorization that we are having, then we can see that we have, in fact, especially 3 categories that are standing out. The first one is A2, and those are the plastic sheets. The plastic sheets were also the one that you could find back here on the picture. So this can be shown as a plastic sheet. It is in fact all different types of plastics that are soft plastic and that can easily bend. So plastic sheets were encountered the most, almost 5,500 pieces over the 240 fields. Then we have category A17, which are in fact the hard plastic particles or fragments of non-foam plastic, also called like that. And then here we also have A20, which is the crisp package and the sweet wrappers that were also encountered in quite a high number on our different fields. Now, if we then have a look into the fields, so all of our fields got a field code. MC24 stands for Micos Project, sampled in 2024. And then we have a field number because, of course, all of the information that we are gathered is treated confidential. So we do not show on which location that the data has been taken or where the sample has been taken, and also no information on the farmers. But as we can see here, for example, if we have a look based on the number of particles into which 3 fields have the highest pollution, we can see that this is field 92, 65, and 141. So maybe remember those. So this is the top 20 that I'm showing you. But of course, we take these microplastic particles by running from point A up to point C. And for this, we take the entire field into account. But one field can be very small, while another field can have a size of about 50 hectares. So we should take also this into account, because maybe field 92 is just a very big field where then the chance of finding plastic particles is of course much higher. So if we also take into account the field size, then we can see that the top 3 of our fields is going to be completely different, where we have even into field number 18 a very high prevalence of plastic particles. And that's because we were only able into this field to sample about 6 squared meter. And I think field 18 was also already able here. So on 6 squared meter, we had already 108 plastic particles. So this was a highly polluted field, which of course explains, if you then put it on plastic litter per hectares, that you're encountering in the end of about 270,000 plastic particles present on one field. And I've sampled this field by myself, and for me, I think this number seems quite right, because it was very, very, very polluted. So taking into account also the different size of the fields, of course, we get a different number in here. But as you can see already from macroplastic pollution, and I think we are the first one who are doing this, especially in such a big number, we can already find a lot of different plastics back. And based on our Excel file, of course, we also hope to really designate where that these big plastic particles are coming from, which will be more easier compared to the microplastic parts. And then we are wondering if we are going to see a similar result, and if the same 3 fields that are very highly polluted, if this will be the same for the microplastic pollution as well. And this brings me almost to the end of my story for today, because we are now still working a lot into the risk assessment. So I've shown you how we have optimized a method to measure microplastics into a soil environment, and how we did a large-scale measurement plus the first results. But of course, the story will not end with this. We will then move onwards to the risk-based testing, where we especially going to start up greenhouse experiments, taking into account the concentrations that we will find back from these large-scale measurements, to have a look into the effects on plant and soil health. But this will start normally in January 2026, but our PhD student, Josephine, has already set up some small experiments with soils of which we expect that they have a high pollutions, and soils that will have a lower pollution. And we are just sowing now cresson onto these different pots, and seeing if there is a difference in the number and in the biomass of the cresson based on highly and less highly polluted fields. This was just the first test. I am not going to say already any results, but I think that you can see that there is already quite a difference into the plant growth in here by the presence of highly polluted fields and non-polluted fields. And in the end, of course, we also want to know if microplastics are a hotspot. So if a certain type of biofilm is formed onto our plastic material, if certain bacteria or fungi are going to attach to our plastic itself, and if we can find plastic degrading microorganisms. And this work has also started recently, where we have now made media containing polypropylene, polyethylene, PET, and also biodegradable plastics, and where we are now growing different types of microorganisms on to see if we can see any degradation yet already on this media, for which we will then transact further to liquid growth media. But this is, of course, again, a work in progress. And this brings me back then to where I've started into the podcast episodes. And I don't know if I need to say the answer, but I think a lot of you are not native Dutch speakers, and therefore will not be able to listen to the microcast. However, I do advise to do so, because I also tell a lot more than just those 4 questions here. But I think for those of you who have listened quite thoroughly, that's the 3 true statements are the last 3 ones. And it is the first statement that was false in this case, because microplastics are in fact not only smaller than 1 millimeter, but can be, depending on the definition, smaller than 2 millimeter or even smaller than 5 millimeters. So this means that when you're going to eat an apple, that you will eat more plastic fragments than when you will eat 1 kilograms of mussels. In fact, one apple can contain up to 20,000 plastic particles, depending on which type of apple that you're going to buy. Because, for example, if you're going to buy a Jonagold apple here in Belgium, it will be less. But if you would buy a Pink Lady, it will be much higher because Pink Lady needs to be transported from Australia towards Belgium. And to be able to transport this and to keep the apple as fresh as possible, they spray a thin layer of polyethylene on the apple itself. So if you've then are going to eat your apple, of course, with the peel on it, then you will eat a lot of polyethylene. And with that, I'm going to end my talk here. This is in fact my whole team. So we are especially focusing on microplastic pollution, but there are also some people in the team like Josephine, Matthijs, Noor, and Puya that are focusing on plant microbe interactions. If you would be having any more questions, of course, you're welcome to send an email to me. I think I can answer most of the general questions, also the project overview. I'm also responsible for the project coordination. But if you want to have a little bit more in-depth knowledge, for example, into the microplastic measurements or the plastic degraders, I would advise you to send an email to Bente van Buiten, who really designed the technology. Everything about sampling procedure, soil analysis, and soil microbiomes, I refer to Lisa Joos, who really is an expert in soil health. And then if you want to know a little bit more about the greenhouse experiments that are going to be set up and how we are going to measure the effect of microplastics on soil and plant health, I advise you to send an email to Josephine de Meulenaren. And with this, I'm going to end my talk. Thank you for being here, especially because this was a quite long talk of about 1 hour. And of course, if there are any questions, I will be very happy to answer them.
Okay, Caroline,